Hello everyone, my name is Aaron Carmen and I'd like to welcome you back to my series of videos covering basic circuit analysis. Today, in Lecture 3, we'll be going over Kirchoffs laws. So in order to accurately analyze circuits, we have to establish some ground rules to make sure that the results we get are feasible in the real world. So the first thing we're going to talk about are the wires in a circuit. So before we had just a little circuit like this with a voltage source and a resistor. So let's just put arbitrary values here. So these wires here and here, we never really talked about those. So those wires are going to be perfect conductors. So that means that if it was just the wire, that the wire is not going to provide any resistance at all. So from this point to this point, there's no resistance at all. Okay, so because there's no resistance, that means there's never going to be any voltage drop. So you remember Ohm's law, V is equal to I times R. If R is 0, then the voltage is going to be I times 0 ohms, and that's always going to be equal to 0. Okay, so that means that the voltage on any point in the wire is always the same. So if this has 10 volts here, it's going to have 10 volts here as well. So there's not ever going to be any voltage drop on the wire. Okay, so now that we've gotten that out of the way, we need to establish the conservation of energy and power, as well as charge. So in order to understand this in an electrical sense, we are going to be using Kirchoffs laws. So there are three sets of laws that we'll use. They're called Kirchoffs voltage law, Kirchoffs current law, and Kirchoffs power law. So we're going to start with Kirchoffs current law. So for Kirchoff's current law, what it is stating is that the current coming into a node has to equal the current leaving the node. So we can think of this as the conservation of charge. Conservation of charge. Because we can't just create charge out of thin air. It has to come from somewhere and it has to go somewhere. Okay, so if you think that we have a node like this. So there's 3 branches on this node. And say that there's a current this way, a current this way, and a current that way. So there's 2 currents entering the node and 1 current leaving the node. So let's call this IA, IB, and IC. Okay, what Kirchoff's current law is going to say is that it will say that the sum of the currents entering, so IA plus IB, has to equal the sum of the currents leaving. Okay, and this isn't just in a 3-branch case. This could be any number of branches. The amount of current that's entering is the amount of current that's leaving. Because remember, current is actual charge that's moving. So if you have a certain amount of charge entering, that same amount of charge has to be leaving. And if you don't get that answer, if Kirchoff's current law isn't satisfied, then you did something wrong. Okay, so if we look at this a little bit different way, if we write IC instead as current entering the node, so IC, then IC would then be on this side, and it would have to be equal to 0. Okay, so how does this make sense? If we have all these currents entering on the node, we have to have some current leaving, right? Well, why don't we have the arrows pointed outward? And that's because, remember, whenever we talked about current, it has a direction. And since we flipped the direction on IC, this sign is going to change. So if it was 1 amp before, it would now be minus 1 amp. Okay, so having that negative number in there will help it reach 0. So it's mathematically allowed. So now that we've talked about Kirchoff's current law, this is also called KCL. You'll hear me call it KCL. Now that we've talked about Kirchoff's current law, we can talk about Kirchoff's voltage law. Now, similarly to KCL, this one's also called KVL. KVL is the conservation of energy, right? Because we can't just create energy out of nowhere. It has to come from somewhere and it has to be used up somewhere. So what Kirchoff's voltage law is saying is that around any closed loop in a circuit, the sum of the voltage rises and the voltage drops is going to be equal to 0. Okay, so let's just get a very simple circuit here to look at this. So let's start off with the simplest circuit we can do. Just a voltage source and a resistor. So let's say 10 volts, and let's just say this is a 10 ohm resistor, and we'll fully define it. So this is 1 amp. So that must mean that using Ohm's law, let's say the voltage across the resistor is equal to the current times the resistance. So that'll be 10 volts. So there's 10 volts across this resistor. Now, if we look at the only closed loop around here, so if we start from this point, let me switch up my marker. If we start from this point, go around it, at that point we've just gone over wire, so there's no voltage drop on the wire. And then once we go across the resistor, we have a 10 volt drop. Okay, so let's make a note of this. So we've had a 10 volt drop, okay, and we're using a positive 10 volts because remember from the first lecture we said if it's a drop, it's positive, and if it's a rise, it's negative. Okay, so now we've got that 10 volt drop. We'll keep going. This wire doesn't add anything because it's just a wire. It's a perfect conductor. And then here, we're entering at the positive on this voltage source, or entering at the negative, excuse me, and then coming out the positive. So that will be a 10 volt rise. Okay, so then we have minus 10 volts. Remember we said that the sum of the voltage drops and rises has to be equal to 0. Okay, so this is showing that for this circuit, Kirchoff's voltage law is satisfied. Now, what if we make this just a little bit more complicated? Let's say that now we have the same 10 volt source, the same 10 ohm resistor right here. Okay, and then we also have, let's just say, another 10 ohm resistor. Okay, so we're not going to analyze the currents or anything like that, but what we can say is that in this loop, if we start here, let me switch back over to red. If we start from this top corner, we are going, and we're going to see a voltage drop across the resistor, and then a voltage rise of 10 volts there. So using this information, we can say the voltage drop on that resistor has to be 10 volts. So let's just say the voltage on the resistor, okay, and then minus the 10 volts from the supply has to be equal to 0. Okay, and then using this, we can say, okay, voltage on the resistor has to be equal to 10 volts. That's the only way that it'll be satisfied. All right, now let's try a different path. So if we, well, let me just undo all this. So if we instead, let's start at the same point, and we have to follow a closed loop. So let's go along this way. We've just gone along wire at this point, and then we drop across this resistor, come back around, and that's a closed loop there. So we can say again, we'll have the voltage on the resistor, let's use R2, minus the 10 volts from the supply has to be equal to 0. Okay, so using this same stuff, we can say that there is another 10 volt drop on the second resistor. All right, well, let me go back to it. Now for this last one, we've only talked about loops that have the source in it. Okay, but let's go ahead and make some notes here. Let's say we have plus or minus 10 volts, because that's what we found, and then we also have plus or minus 10 volts, plus minus 10 volts here. So there's a drop from the top to the bottom on both of these resistors. Okay, so now if we start from this point, let's say, we go along, we're doing a drop across this resistor, right, because we're coming into the positive, so there's a 10 volt drop across that resistor, so 10 volts. We're going along this wire, it's a perfect conductor, so there's no voltage. All right, and now instead of going to the source this time, let's go up through this resistor. Okay, and then that creates a closed loop. Now, for this resistor, are we going to call it a voltage drop or a voltage rise? Well, in order to answer this question, we have to look and see we're coming in on the minus terminal of the resistor. Okay, so since we're coming in on the minus terminal and coming out the positive, it has to be a voltage rise. So it'll be minus 10 volts. Okay, and then that's equal to 0. Okay, and this satisfies Kirchoff's voltage law. So basically what Kirchoff's voltage law is saying is that no matter what path you take, you'll always come back to the same point on that path. If it's a closed loop path, you'll come back to the same point on any path, and it will be the sum of the voltage rises and voltage drops will be equal to 0. Okay, so this is the conservation of energy, and it's saying that no matter what path you take, as long as you come back to where you're at, there will be no voltage change. Okay, and that's important. Okay, so the last thing that we're going to talk about, let me switch back to black now, is Kirchoffs Power Law. So Kirchoffs Power Law. Okay, and then we'll also call this KPL. Okay, so just like KVL, this has to do with the conservation of, well, it's a conservation of power, but it's very similar to the conservation of energy. So qualitatively, what Kirchoff's power law is saying is that if we have power being dissipated in, say, like a resistor, so if power is being dissipated by a resistor, something has to be supplying that same amount of power. So what Kirchoff's power law is saying is that the sum of the power being supplied has to equal the sum of the power being dissipated. So let's go back to our very basic circuit. So we have, let's say, just a 10-volt source and a resistor. Oh goodness, that looks terrible. Let me make that look a little bit better. So we have a 10 ohm resistor and a 10-volt source. Okay, and then we know from before that there's 1 amp of current flowing through it. Okay, so now power is equal to voltage times current. So there's a voltage drop here of 10 volts. So let's say the power in the resistor is equal to that drop of 10 volts times the current of 1 amp. Okay, so then the power in the resistor is going to be equal to 10 watts. Okay, and this is a positive number, so that means that power is being dissipated. Okay, now let's look at the power in the voltage source. So remember, since current has to be conserved, there's also 1 amp coming here because it's a closed circuit. You can't just get rid of that current. So if we say power in the source, okay, it's going to be equal to the voltage again times the current. Okay, so we're going to keep the current positive, so let's just put the 1 amp here. Okay, and now it's a 10-volt source, but are we going to use plus or minus 10 volts here? Well, since the current is going into the negative and coming out of the positive, it's going to be minus 10 volts because it's a 10-volt rise. Okay, so this means that PS, the power at the source, is going to be minus 10 watts. Okay, so this means it's supplying 10 watts while the resistor is dissipating 10 watts. So now if we look at the sum of the power in the entire circuit, we have PR and we also have PS. Okay, and this has to be equal to 0. And in this case, we have 10 watts for PR minus 10 watts for PS, and that's equal to 0. So this satisfies Kirchoff's power law. So just as a quick summary, let's go back through these notes real quick. We can see that current law is the conservation of charge, and that this is just saying that the current entering a node has to be equal to 0. And using the fact that a negative current means that it's in the opposite direction, we can equate this to say that the current entering the node has to be equal to the current leaving the node. Okay, Kirchoff's voltage law says that along any closed loop, the sum of the voltage drops and the voltage rises has to be equal to 0. So the number of voltage drops has to be equal to the number of voltage or the amount of voltage rise. Okay, so this is important to note because if this isn't satisfied, then we're just creating energy out of nowhere, and that's something that we can't do. So it's important that we satisfy KVL as well. And lastly, we have Kirchoff's power law, which just says that any power that's being dissipated in this circuit has to come from somewhere, and that that power that's being supplied has a negative value, so the sum of all the powers in the circuit has to be equal to 0. So again, this just means that if you have power being dissipated, it has to be supplied from somewhere in that same amount. So if you're dissipating 12 watts and supplying 15 watts, then something's wrong there because you have an extra 3 watts that's unaccounted for, and everything has to be accounted for in this circuit. And if it's not accounted for, then we've done something wrong. So it's important that we know KVL, KCL, and KPL, and that we check and make sure that it's satisfied for every circuit that we analyze. So in the next videos, we're going to be looking at different combinations of resistors. We're going to start off with series combinations, which is just 2 resistors connected in series. So I'll just go ahead and make a note here. We're going to be looking at combinations of resistors like this. So that's a series combination. And then we're also going to be looking at combinations of resistors like this. So that's a parallel combination because these two are they look like parallel lines, and these are in series with each other. Okay, so we're going to be looking at those combinations. We're going to need to know KVL and KCL whenever we're looking at all of these, so it's important that we have these concepts or that we remember the equations and that we're good on the concepts of KVL and KCL. And then KPL, we're just going to be using to check our answers and make sure that the answers that we have make sense. So thank you for making it to the end of this video, and I hope to see you in the next ones. And if you have any questions or suggestions for these videos in the future, please feel free to leave them in the comments below. I'd be happy to look at them and improve these videos in any way I possibly can. So I hope to see you in the next ones.